This is your presenter Asloob Mudassar, and I am presenting slide number 91 of the course on laser physics. Question is, in the designing of a stable laser resonator, the laser spot size, thermal fluctuations in the active medium, pumping power are the key consideration points apart from the cavity parameters. Discuss the designing of a stable resonator. The answer is, so before I answer, let me have a look at the figure number 1. So this is figure 91.1, and the caption is a typical two mirror resonator containing a thin lens to simulate the thermal effects in an active medium due to pump power fluctuations. So you see that this is a two mirror cavity resonator having spherical mirror 1 and spherical mirror 2. The dimensions of these mirrors is 2A1 and 2A2. The separation between the two mirrors is represented by capital L, and the separation from the lens is represented by L1 of the mirror 1 and by L2 of the mirror 2. R1 and R2 are the radii of curvature of the spherical mirror 1 and spherical mirror 2. So you see that you can see a lens within the resonator of a focal length f and the aperture size 2a. This lens has been placed in order to simulate the thermal effects in an active medium due to pump power variations. You see that in the laser you need optical pumping. So when the optical pumping, the power fluctuates in the optical pumping, then you see that due to that one, thermal effects are produced within the resonator. So to simulate the such thermal effects, we insert a lens of a focal length L of diameter 2a within the resonator. The change in the focal length of the lens will actually help us to simulate the thermal effects in the active medium due to the pump power variations. So I think that the description of the figure is complete. So let me read the statement. In a laser cavity, it is desirable that the size of the beam spot should be comparable to the transverse dimensions of the active medium. The transverse dimensions mean that the dimensions which are perpendicular to the optical axis which we have shown joining the two mirrors. So the transverse dimensions will be perpendicular to this optical axis, that is the x direction and the y direction. Such a resonator is designed with the cavity G parameters close to G is equal to plus minus 1 point. So you see that this G parameter is actually a product of two quantities, G1 and G2. And G1 is related to the lens L1 to the mirror 1 through the relationship that G1 is equal to 1 minus L over R1. And G2 due to the mirror 2 is represented by G2 is equal to 1 minus L over R2. This is what we have discussed in one of the previous slides. So such a resonator is designed with the cavity parameter G close to the value that G, which is the product of G1 and G2, is equal to plus minus 1. That is as a near planar or a near concentric resonator. So you see that the resonator which are lying close to the curve drawn by the mathematical equations G1, G2, or G is equal to plus minus 1, that curve is a curve where we have two resonators, near planar resonators or near concentric resonators. That is, the resonator has to work on the edge of the instability boundary. This makes the cavity very sensitive to variations in pump power. So you see that this curve, which is the G is equal to the curve due to G is equal to plus minus 1, which is in principle actually G1 multiplied by G2, is the product is equal to plus minus 1. So that curve is actually the curve where beyond which the system becomes completely unstable. So this is the instability curve. And we are and over resonators, which is a near planar resonators containing two planar mirrors, for example, or the near concentric resonators. These two resonators lie along the lie very close to this curve. So for that one, you can see one of the previous slides where I have discussed the stability of resonators. Let us discuss a laser resonator designed for large spot size and at the same time insensitive to pump power fluctuations and any sort of mirror tilting during operation. So you see that here we are addressing two things: insensitive to pump power fluctuations and insensitive to any sort of mirror tilting. So you see that in order to simulate the power fluctuations due to the pumping or the thermal variations or the thermal effects, we have inserted this lens. And you see that we can change the focal length of this lens. When you will change the focal length of this lens, what will happen? The spot size, what will happen? The mirror, the beams will becomes out of aligned. The alignment is lost. So the mirror 1 and the mirror 2 are adjusted in order to align the laser spots within the cavity. So misalignment may occur. So this is what we want to address the two things. That is, we want to have a spot size which should be insensitive to the power fluctuations and also to the insensitive of any sort of mirror tilting during operation. The pump power induced fluctuations produce thermal effects in the active medium, which can be simulated by a thin lens of dioptric power equal to 1 over F, proportional to the pump power as shown in figure 91.1. So you see that here we are using a lens of dioptric power equal to 1 over F, and this dioptric power is set proportional to the pumping power, and by which we can change the focal length of the lens. That is, we can change the dioptric power according to the allowed variations in the pump power, and this is how we can simulate our system. In the designing, the following constraints are imposed. Constraint number 1, the spot size in the active medium represented by WA should remain unaffected by the thermal variations in the active medium, or equivalently by the variations in the lens dioptric power. So you see that this is our requirement, that our spot size should remain unchanged or unaffected by the thermal variations in the active medium, or which is equivalently represented by variations in the lens dioptric power in our system. So that point 1 can be addressed mathematically as the derivative of WA with respect to 1 over F, that is dWA over D of 1 over F is equal to 0. That is, we want to minimize the variation in the laser spot size or the spot size WA with a change in the dioptric power of the lens, which is 1 over F. And this is equation number 1. Resonators meeting this condition are named as a dynamically stable resonator. Now the condition 2 is the beam spot size WA should be smaller than the transverse dimensions of the active medium. Here we are assuming that our active medium has a diameter of the order of 2A. To avoid beam truncation, that is, WA is equal to 2A over pi. So you see that 2A is the diameter of the active medium rod, and WA is actually the spot. We want this spot to be smaller than, since this is a spot in radius, so we want this to be less than the half of the diameter. So we have divided 2A by pi to keep the things on the safe side. So this is our laser spot WA, which is related to the diameter of the which is related to the transverse dimensions of the active medium by the relationship that WA is equal to A over pi. And you see that 2a is what we have also shown as the dimensions of this lens, because this lens has the dimensions of the diameter of the active medium rod. So we have obtained conditions number 1 and 2. Four cavity designing parameters R1, R2, L1, L2 appear in the last two equations with the two fixed parameters A and F. So you see that R1, R2, L1 and L2 appears in equation number 1 and 2 implicitly. Obviously they are not present, but you see that if you represent WA, which is the beam waste in terms of the parameter G1 and G2, this is what we have discussed, beam waste measurement of the laser resonators in one of the previous slides. You can have a look over there, and then you see that WA can be represented in terms of G1 and G2. And you know that G1 and G2 are related with 1 minus L over R1 and 1 minus L over R2, or equivalently in terms of L1 and L2. So you see that we have implicit dependence of the parameters R1, R2, L1 and L2 in these two equations. The plot of WA versus 1 over F is shown in the figure 2. So this is the figure. You see that on the vertical side, we have plotted the spot size WA, and along the horizontal axis, we have plotted 1 over F, that is the dioptric power of the lens. And you see that we have shown delta, two regions represented by zone 1 and zone 2. The width of these two zones is represented by delta in each case. And the delta is a function of 1 over F. That is, delta is a function of the dioptric power of the lens. The caption of the figure is a plot of spot size WA and the combined mirror misalignment SC versus the dioptric power 1 over F of the cavity. So we have drawn two parameters. One is the WA versus the dioptric power of the cavity 1 over F. So you see that you will notice there are two zones, zone 1 and zone 2. And you see that WA is represented by the solid curve within zone 1 and zone 2. So WA becomes much greater if you move away from the center of zone 1 on either side. And similarly, if you move away from the center of zone 2 on either side, WA will increase drastically. At the center of zone 1 and zone 2, the spot size is minimum, which we have represented by a line, by a dotted line horizontally drawn, and that represents WA minimum. So this is the minimum spot size, which corresponds to the center of the zone 1 and zone 2. And you see that there is another parameter SC. SC is actually the parameter that represents the combined mirror misalignment. So you see that when we change the dioptric power of the lens, the SC parameter initially is very small. For example, in the zone 1, its value is small. But if you go further up to the zone 2, it becomes very large. And what we want in our designing is that we want that over misalignment error should be much smaller, so that it should not affect the values of the spot size of the beams. So we want SC to be as small as possible, and probably in the region zone 1 we can take the value of SC to be reasonable. So we have explained the two plots over here. One is the laser spot WA versus the lens dioptric power of the resonator, and secondly the combined mirror misalignment represented by the parameter SC as a function of the dioptric power of the lens. There are two stability zones, each of width delta as a function of 1 over F, giving two equal minimum values of WA labeled as WA minimum, lying in the center of zone 1 and zone 2. The beam spot diverges at the boundaries of the two zones. This is, you can see that the beam WA, that is a beam spot, diverges when you move away from the center of zone 1 and the center of zone 2, because the values become much larger. The WA minimum satisfies the condition WA minimum square, that is the square of WA minimum, is equal to 2 times lambda divided by pi into delta, and delta here is a function of 1 over f. So this is shown in equation number 3. So we have calculated over here the minimum size of the minimum spot size that is possible for the zone 1, for the in the center of the zone 1 and zone 2. But you see that here zone 1 is over preference, because the value of SC, which is the misalignment parameter for the two mirrors, is smaller for the zone 1. So you see that this is our figure. We can simplify this figure in terms of a more general optical system. So figure 91.1, that the figure that I have just shown you, can be expressed in a more general way as shown in figure 91.3. The A1, B1, C1, D1 is the one-way matrix, and the stability condition is expressed as A1, D1 is greater than equal to 0, is less than equal to 1, in analogy with the stability condition shown in G parameters as the product of G1 and G2 is greater than 0 and less than 1. These two conditions have been addressed in slide number 85 and in equation, and preferably in equation number 7. So you can consult slide number 85 or the question number 85 to have a detailed analysis of these two stability conditions. The figure of the caption 3 is a general optical system representing the resonator shown in figure 1. So you see that we have drawn two parallel planes in front of the mirror, spherical mirror 1 and spherical mirror 2. So these the plane 1 and the plane 2 are just in front of the spherical mirror 1 and spherical mirror 2. And you see that we have shown the direction of the z-axis passing through the center of the mirrors, or the center of the lens that is placed in the resonator. And you see that A1, B1, C1 and D1 are actually the matrix elements A1, B1, C1, D1, which represents one-way matrix for the transmission of the field from the plane 1 to the plane 2. Without proof, we say that A1, B1, C1, D1 are linearly related to 1 over F. You see that here we are talking about linearly related, the matrix elements, The plot of the stability condition with A1, D1 as the axis is shown in figure 91.4. So you see that here we have discussed the stability in terms of the parameter A1 and D1. And here we are plotting in this figure. For example, A1 is plotted along the horizontal direction, and D1 is plotted along the vertical direction. So you see that if you plot the lens dioptric power in this plane, that is in the plane determined by A1 and D1, you will notice that it will be a straight line. You see that there are two curves. One is in the first quadrant, the other is in the third quadrant. These curved lines are due to the product of G1 and G2. So these are the G1 and G2 curved lines. In the first quadrant, G1 and G2 both are positive. In the third quadrant, G1 and G2 both are negative. But the product of these two quantities is positive. Both for the curve in quadrant 1 and for the curve in quadrant number 3. So you see that we have indicated zone 1 by the two, and the extreme ends of the zone 1 are represented by two black dots. One is on the instability curve represented by the parameter G1, G2 is equal to 1, and the other is lying on the vertical axis, for example on the D1 axis. Similarly, we have represented the zone 2 by the extreme end of the zone 2 represented by two dots. One is on the horizontal axis A1, and the other dot is on the instability curve in the first quadrant represented by the product of G1 and G2 is equal to 1. You see that corresponding to these 4 points, 2 points corresponding to zone 2 and 2 points corresponding to zone 1, we have drawn the resonators. So there are two resonators corresponding to these two extreme points of zone 1, and similarly there are two resonators shown corresponding to the two extreme points of zone 2. So zone 1 and zone 1, these 2 points are the extreme points lying, you see that in the instability region, because the stable region lies between these curves due to G1 and G2 is equal to 1, and between these axes, that is the A1 axis and the D1 axis. So this is the curve, the region between the curve and these axes is actually the region where the stability of the resonator is important. So the resonator will be stable in these regions, that is in the region between the axis and the instability curve, and the region over here between the axis and the instability curve. So we have chosen these two extreme points on zone 1 and these two extreme points on zone 2, where we have a marginally where we have the resonator with marginal stability. Okay, so let me read the caption of figure number 4. Stability curve of a general resonator with straight line showing a linear relationship between D1 and A1, where A1, B1, C1, D1 is the one-way matrix of a general resonator. Zone 1 and zone 2 are also shown, and the resonators at the boundary points of these zones are also specified. That is, we have also specified resonators corresponding to each zone. When 1 over f is changed, D1 and A1 are found to be linearly related, which is represented by a straight line intercepting the stability curve at 2 points. The line also interrupts the coordinate axis. Zone 1 and zone 2 have been labeled in the figure. Laser resonators in general forms corresponding to the 4 points are also shown. We have a relationship relating the dioptric power of an optically pumped rod and pump power absorbed PA in the rod as the active medium through the relationship. So 1 over F is equal to K over pi A square multiplied by PA, where PA is the pump power absorbed in the active medium rod, and 1 over F is actually represents the variation in the power of the pump, and we have declared it as the dioptric power of an optically pumped rod, because this lens has been used in order to simulate the variation in the power of the pump. And the relationship between these two quantities, that is the dioptric power of the lens and the energy and the power absorbed in the active medium, these two are related through the constant K over pi into A square, where you know that A is the radius of the optical rod, and rest of the quantities are clear, where k is a constant that depends on the material characteristics. It is not the wave number, so it is another constant which represents the material characteristics. The range of acceptable absorbed pump power, so you can, if you want to calculate the range, then you need to take delta PA in equation number 4, and of course on the left hand side you will take delta 1 over F. So you have delta PA and then you have delta 1 over F. If you move delta PA and solve equation number 4 for delta PA, you have delta PA is equal to pi A square over K multiplied by delta into 1 over F. Delta, this is not 1 multiplied. This is a delta function, delta as a function of 1 over F. So delta PA is equal to pi A square over K multiplied by delta of 1 over F, as shown in equation number 5. So this d delta PA provides you a range, acceptable range of the absorbed pump power as a function of the change of the dioptric power of the lens. So this becomes constant for a given laser material when A and delta of 1 over F are eliminated using equation number 2 and equation number 3. So you see that equation number 2, we can eliminate A. The parameter A can be eliminated using equation number 2, and the parameter of delta of 1 over can be eliminated using equation number 3. So then you see that we can have this independent of A and delta of 1 over F. Next, we try to investigate which of the two zones should be chosen to design the laser resonator as less sensitive to mirror misalignment. So you see that now we are going to discuss the mirror misalignment, that how we can make this parameter less sensitive, because this is the requirement of resonator, of our designed resonator, that we should design our resonator in such a way that the resonator becomes less sensitive to mirror misalignment. The misalignment sensitivity S1 and S2 for mirror 1 and mirror 2 are defined by. You see that this misalignment of the mirror 1 and mirror 2 will arise when you will change the dioptric power of the lens. Then of course the misalignment will occur, and these misalignment for the parameters 1 for the mirror 1 and mirror 2 labeled as S1 and S2 are given in equation number 6a and 6b. So S1 is equal to delta R1 C1 divided by WA multiplied by delta of theta 1, and S2 is equal to delta R C2 divided by WA multiplied by delta theta 2, where delta R Cx is the displacement of the center of the beam spot from the center of the rod. So you see that if the center of the beam spot coincides with the center of the rod, then S1 and S2 will be 0. But you see that due to the misalignment, when the dioptric power of the lens is changed, the misalignment will occur, and then delta RC1 and delta RC2 may not be 0. So in that case, the misalignment will occur. And you see that where delta RCX, we have used over X here because X stands for 1 and 2, 1 for mirror 1 and 2 for mirror 2, where delta RCX is the displacement of the center of the beam spot from the center of the rod. When the mirror X undergoes a tilt, delta theta is a tilt of the mirrors, where X is equal to 1, 2. So 1 stands for mirror 1 and 2 stands for mirror 2. The combined misalignment due to the two mirrors is given by SC is equal to S square root of S1 square plus S2 square. So this is the combined misalignment of the due to the two mirrors, and this is what we have plotted in this diagram. That is in figure number 2. We have plotted S2. This is the combined misalignment due to two mirrors as a function of the dioptric power of the lens. Okay, so SC, plot of SC versus 1 over F is also shown in figure 2. SC has much lower values for zone 1 than zone 2. Thus, resonators in zone 1 becomes less sensitive to misalignment because the beam spot sizes are much reduced for the resonators in zone 1. The lower stability point in zone 1 corresponds to a resonator with very small spot size Wm due to beam focusing on the two mirrors, with the corresponding beam divergence is very large. You see that the divergence of the beam is related with the focusing, or is related with the beam spot size through the relationship, that is theta is equal to theta d, where theta d is the divergence angle, or the divergence of the beam is given by lambda over pi into Wm, where Wm is the minimum spot size that you can achieve in a resonator. So you see that the smaller the value of Wm, the larger the value of the theta d. And you see that we can obtain theta m smaller when the beam is focused on the two mirrors. So the resonator is designed in such a way that you have a focused beam on the two mirrors. So this minimizes the spot size Wm, and at the same time it maximizes the value of the divergence of the beam theta d given by this relationship. The misalignment will be effective when mirror tilt angle is a significant fraction of theta d. So you see that the tilt should be a significant fraction of theta d, then the misalignment will be important. If it is a small fraction of theta d, we can ignore the misalignment. The misalignment will be effective when the mirror tilt angle is a significant fraction of theta d. And you see that the mirror tilt angle are given as theta as a delta theta 1 and delta theta 2 in equation number 6a and 6b respectively. The misalignment will be effective when mirror tilt angle is a significant fraction of theta d. Practical considerations reveal that a resonator should be designed at a value lying in the center of zone 1 rather than the parameters dictated by equation number 1. So you see that we shall not concentrate in practical sense. Although mathematically it is required that equation 1 must be followed, but practical sense reveals that it is not important to follow the equation 1 for the efficient designing of the parameters. The parameters can be designed efficiently when we consider the center of the zone 1. In zone 1, let L1 has limiting values L1 prime and L2 primes. Then the following conditions must be satisfied. So L1 prime and L2 prime are the two parameters that decide the range of the placement of the mirror 1 with respect to the lens within the resonator. So L1 prime is the smaller value and L2 double prime is the larger value. So these two provides you the limit for the placement of the mirror 1 with respect to the lens of the lens placed within the resonator. So these two L1 prime and L2 prime must satisfy this condition as shown in equation number 7. So 1 over L prime plus 1, so 1 over L1 prime plus 1 over L2 is equal to 1 over F. So you see that this is very similar to the geometric equations in which L1 prime represents the object distance and L2 prime represents the image distance or vice versa. It means that the beam is being focused from L1 to the distance from L1 prime to the L2 prime. So it means that we have a focused beam on the two mirrors. So the extreme case is that 1 over L1 double prime minus R1 plus 1 over L2 is equal to 1 over F. So either condition 7 is satisfied or condition 8 is satisfied. So these provide you the extreme limits. So any value of L lying between L1 prime and L2 prime can be used to satisfy this equation. So when such an equation is satisfied, it means that the laser spot is being focused on mirror 1 and mirror 2. And you see that under that condition, the beam spot size will be minimum. And when the beam spot is minimum, divergence will be maximum. And when the beam spot size is minimum, it means that we are working in the center of the zone 1, which means that misalignment errors are also reduced. For a given F and PA, a range of delta PA will be permissible, allowing the design to work independently of cavity parameters. So you see that here we shall a range of delta PA will also be permissible and will also be worked out that is within this range, because you see that this is what we have to decide what range we permit in our resonator, in our designing of the resonator. So once we decide the value of delta PA, then of course we can under these two conditions and other the conditions that we shall work under the center at the center of the zone 1, then you see that we have to follow the other equations and then we can design our resonator for efficient resonator in which we can minimize the power fluctuations and also the misalignment of the mirrors, misalignment errors due to the mirrors 1 and 2 when the dioptric power of the lens is changed. So this is the end of slide number 91.